All right, good morning. I think everyone can hear me. I can hear myself quite well. I'm Lukasz, and in the next 45 minutes I would like to show you what happens under a hood when you invoke a parallelStream. So the idea is to show you what happens under the hood, and basically based on this to draw some conclusions. When can you make your applications run faster, when not? I'm a software engineer at CERN for the last 9 years, and okay, so CERN, what is it? It's in a nutshell, it's the world's largest physics laboratory. So basically, we study the building blocks of nature, and well, try to answer serious questions like when was the universe created, what are the origins of it, and so on. And in the physics, it's kind of funny because for the smaller you look, the bigger you need. So how do we do it? Well, by building, maintaining, operating huge particle accelerators. Maybe one of those you know is the Large Hadron Collider, the biggest machine ever built by a man. It's like 17 miles rate, 17 miles long, 300 meters below the ground, and yeah, so it's really placed between the French and Swiss border. A bit farther in the background, you will find the beautiful Alps and the best skiing resorts in Europe, so the key elements in the map. And of course, by doing this kind of things, by pushing the frontiers of knowledge, sometimes there are very nice spin-offs created. So maybe, well, CERN is also the place where the web was born. You probably heard about it. It was invented by Tim Berners-Lee in '89, if I'm not mistaken. So this is the first web server ever, and obviously the gentleman wasn't very fond of switching it off because, well, by switching it off you would switch the whole web off. So well, not the best idea. But okay, as much as I would like to talk more about CERN, we can have a chat afterwards. Let's not keep our CPUs idle. So let's go straight to the business. You don't need to follow what the code does. It's just something to start with. So I think that every one of you would agree that collections are one of the most heavy used APIs in Java. But actually, despite being necessary for almost every Java application, manipulating them, it's always kind of painful. So whenever you have to do something, you always hit like a pain point that, man, why I'm actually struggling again with this. So you know yourself best. How many times did you find yourself re-implementing over and over the same database-like operations, using all these control blocks like all these loops, ifs, and so on? And this is exactly what the Stream API is trying to address. So basically here on the slide you have exactly the same functionality. And it's nice. It really reads like a problem statement, and this is exactly what streams are about. So they are an update to Java API that simply lets you manipulate collections. Well, not only collections, or actually like a sequence set of values in a declarative way. So you say what you want instead of actually how really to do it. If you look for a metaphor, it's like when you watch a movie over the internet. It's like a stream. So the frames, the elements of the stream keep flowing. If you have like a movie on a DVD, it would be more like a collection. If you're into philosophy, a stream would be like a set of values spread over time. And whereas a collection would be like maybe a set of values spread over space, well, computer space in our case. One more example with the stream. Well, what we do here, we have bunch of numbers. We map them. We actually filter only those that are primes. Then we check. We convert them to the binary string. Then we check whether it's a palindrome. So whether if you read it from left to the right or from right to the left, it will be the same. And we count how many we have of those. And actually, although this example doesn't make sense at all, still you need like 5 seconds to figure it out what it exactly does. And this is exactly what the streams are about. But what about its performance? So like, is prime calculating prime numbers? It's kind of a difficult task. Well, it has to be difficult because otherwise all the asymmetric cryptography would break. So it's kind of CPU thirsty. And if you think about the progress in the chip making, So when you look back, so how did the characteristics of the mainstream chips changed over the years? So for like, I don't know, 2-3 decades, we had a very nice times that basically every year, we had this exponential growth in the clock speed. So basically, all you had to do to make this application faster is to go to the store, buy a new PC every year or every 18 months, and voila, it was twice as fast. And well, the life was that good till like 2000 something, when the Moore's law, all it could give you actually were not really faster cores, but more cores. So in order actually to speed up the application, you really had to leverage the multi-core architectures. And I think in Java, it's particularly nice to see how the hardware trends were really shaping the software trends. So if you think about when you go again a bit back in time, so from the very early days, you had the Threads API. It was, well, what it does, it basically forks off from the main execution line, and you can simply execute some stuff in the background. It wasn't about multi-core at this time. It's like, well, beginning and end of 90s, it was more of to make your UI not responsive and so on. And I think that's also the message in the presentation, is that the good old thread, it's still good for certain tasks. If you have like something very, very little you would like to do in the background, well, you still can go for a thread. Because if you apply the parallel streams everywhere, well, you will very quickly make a conclusion that Java 8 completely sucks. And it definitely doesn't. It just, the parallel streams, they have this discrete responsibility to handle CPU-hungry tasks. If we move a bit forward in time, well, JDK5 was quite generous because when the multi-core CPUs were becoming more popular, so you had the concurrent collections, you had the semaphores, you had the blocking queues, you also had the executor service and the thread pools. I just listed it here because we're gonna reference back to it. So the idea of the executor service, well, it's very simple. You have just like a container, a bunch of threads. It's just guys that are waiting for your work. So you just submit the work there, and it will be done for you. So it's gonna take care of this creation, of the creation, management, and execution of the threads. And you can have different variations of the executor service and the thread pool. So for example, you can have with a fixed number of threads. You can have the scheduled one that basically you can send something and say, hey, execute this thing in half an hour, or execute it periodically every 5 minutes. So it was a very nice addition, all that to the API. Okay, if we move forward in time, we land with the parallel streams. So what you saw on the previous slide, this nice and sweet declarative syntax to process your data, your collections, it's just one of the goodies that the streams are about. So what they also let you to do. So on top of that, you can execute those streams almost for free on your multi-core CPUs. So basically, all you have to do is to turn your stream into a parallel stream. So as you can see on the slide, is the code visible in the back? I'm not sure what I do if it wasn't, but well, probably it's polite to ask as well. So basically, on the left side, we have again our nonsensical prime number palindromic example. If the stream runs sequentially, it takes like, well, a bit less than 9 seconds to execute. If I just make it, I have a laser pointer here. If I just indicate that this should be executed in parallel, it's gonna take, well, it speeds up by the factor 5. So how is this possible? What is the trick? Well, the main trick is that with Java Streams API, it employs the internal iteration. again, if we think about the metaphor, when my fiancée tells me to wash the dishes, she can do it. She can apply the external iteration, so she can tell me wash the fork, wash the knife, wash the plate, or she can really, if she has that trust in me, she can say just wash the dishes, and it's gonna me who is going to pick up the plates, the knives, and maybe I can introduce some optimizations. So this is like the main, basically the main trick it does. And in the background, it employs this forkjoin framework and the Spliterator. And this is exactly what we're gonna see in detail. But before that, I told you about turning a stream into a parallel one. So what does it really mean? How do you do it? So we basically have two options. The first is if the stream source is a collection. Basically, all you have to do is to just invoke the parallelStream method on your source. If it's like a generator function or something else, but it still can be actually a collection, you can always, you have this in your stream pipeline, you have this parallel method. And it doesn't really matter where this method is actually, where in your pipeline it is placed. So whether you place it like in the end, or you place it in the middle, it does not really matter. Why? Because when you think about the anatomy of the stream, all those operations, except the last one, are those intermediate operations. So it's very much like the builder pattern. So you just keep saying stuff that what you want to do, but nothing is going to really happen till the terminal operation is going to be invoked. So really the terminal operation is the boss. So it's really, the thing is not going to do anything until we invoke the terminal operation. Okay, so I said before that we have this forkjoin framework, which is the heart of the parallelStream. This is what is being done, this is what is being employed in the background. And let's have a look at it. It was when I did a little time travel before, I skipped it deliberately. So this was added in JDK 5. And yeah, but maybe it wasn't that famous because it's a kind of low level, and I think it's a bit of overstatement to call it a framework, but yeah, it wasn't really me doing it. All right, so what is a forkjoin framework? It's also implementation of the Executor Service, so it's really nothing more than the thread pool with a bunch of threads that you just send that lets you execute your code in parallel. So the major difference, however, comparing to the Executor Service we saw a few slides ago, is that it was designed for a CPU-hungry tasks. So it was really designed to recursively split, fork, process, and finally join the results. So if you think about an example, how does it work? So imagine this can be an array of number, and all we want to do, we would like to add those numbers. And as we have a lot of those numbers, we would like to do it in parallel. So basically what you're doing, it's just the famous divide and conquer. You just partition the array till it will be small enough that you will conclude, okay, actually it's not worth anymore to execute it, to parallelize it further. I do it sequentially, and then, this is where the steps jumps in, and then of course, you did the divide step, now we need to conquer it, you simply join those tasks. To carry on with this example, I think it's not even crucial really to follow all the code. It's more again about the idea how it works. So as I said, we have a forkjoin framework, which is an implementation of the Executor Service. So we must send it. We must send it a task. Please do it. And of course, so first we must implement the task. So basically, you always should, you must implement, it must be either the instance, your task must be the instance of the recursive task or a recursive action. The difference is if it's a recursive task, it returns a result. If it's not a recursive, if it's a recursive action, it doesn't return a result. So it's like a consumer, it just does something, but it doesn't do anything. I think on the Oracle website, when you have the article about parallel streams, they have a very nice example that they have an array of some numbers of like a picture, and they blur the picture, and this would be like a recursive action because you don't return anything, you just process the array. Okay, but in our case with the numbers, we would like to sum them up. So there is only one method that we need to implement, which is implement override. That we need to override is the compute method, and it's a kind of simple approach. So first we see what is the length of our task, and then we have this, the choice to make. If it's small enough, okay, I don't bother dividing it further. However, if it's still big enough, so it's worth to parallelize it, I just do it. So basically, we just created the same two tasks. We pass the same numbers. However, the left task will have the left half of the array, the right task the right half of the array, and we simply execute it. We fork it. So on our left task, we call the fork method, meaning call this asynchronously. And on our right task, we can either call the fork method again, but actually, as we are already in the thread, we do not need to do any more for the time being with it. We can also compute it synchronously, and then we wait when two of them are done, and combine the result. Again, it's not so crucial really to understand it. It's just the idea. So we have our task. So right now we need to submit it somewhere, and this is the fork join. This is the fork join pull. And okay, so what do we do here? So we instantiate our sum method. We create the instance of the fork join pull, and this is kind of already crucial for the parallel streams. So you have two options. So either you create a fork join pull on your own. You instantiate it with a constructor. You supply how many threads, how many of those guys that will be doing the job for you should be there. Or you can use the common pull instance. It's very much like a singleton. So, and what is characteristic for the parallel streams is that they always use the same common pull instance. So they always all the time. Doesn't matter how many parallel streams you have running, how many of them are running in the background. They always use the same thread pool. You might actually ask yourself, okay, like, what the heck with the fork join framework? Because basically we did all the job on our own. Yes, it is a kind of low level thing. However, it has few characteristics that are crucial also for the parallel streams. So first, as you saw before, we have this fork and join method that we can nicely fork off and join it. And it also applies this, and this is actually like really the main characteristics. The fork join pull applies the work stealing algorithm. So basically, in your fork join pull, you have like a bunch of threads. How many we will see in a moment, and those guys. Well, each thread has a queue of tasks it has to execute, and if a certain thread runs out of the tasks, it is greedy. So it's simply looking for in other threads queues if there is something to do. And this kind of, if you were wondering, like in the previous example, what happened if my left or right task would be finished before the other? Well, it's not a big deal, because if it will be finished way before and will be bored, well, it's not going to be. It's gonna steal the tasks from other threads. Okay, again, all the parallel streams they use really one and the same common pull instance. You might wonder, okay, how many threads we have there? The number of it, the number is number of your CPUs minus 1. Okay, why actually minus 1? Why? What happened to the last core or the last CPU? The thing is that this is how the library is designed. That also the thread that submits the task to the fork join pull, it's also becoming a worker. So at the end, it's this -1 + 1. So technically, effectively, you have the number, your common pool is going to work with as many threads as you have CPUs in your PC. If you would like change those, well, you can use this property to set it. But again, if you think about it, that the parallel streams, they should be executed, well, they should really take care of the CPU-hungry tasks. I'm not really sure if it makes sense, because if you create more than you have CPUs, well, it just would be like a certain cost, just an overhead. Also, as the common pool, it's a kind of a singleton. Of course, when you do it, you must always do it before you actually invoke your first parallel stream. So you cannot fine granulate it. Okay, let's execute this parallel stream with 2 cores, change this parameter to 8. Let's execute it with 8 cores and so on. No, it doesn't work this way. Once you invoke your very first parallel stream, this won't be considered anymore. So probably you should pass it like on the command line. Okay, so I kept repeating for like 500 times that parallel streams, they always use the same instance of the forkjoin pool. The question is, can you use your own? So can you say, okay, this parallel stream should be included, this should be executed really with this one and only forkjoin pool? The answer is yes. However, I just show it for the completeness sake, because it's something I wouldn't really do. So how do you do it? Well, if you look at the fork method, what it exactly does, this guy is a kind of context sensitive, so that if it's already running in a certain pool, it's just gonna stick to there. So basically, the trick is to create your fork join pool with as many threads as you want, and then simply submit your parallel stream execution there. And again, shown for completeness sake, it's not something what I would really do. You probably can, well, if you look for reasons to do it, well, I'm against it, but I'm trying to be as objective as possible, like a kind of lawyer or something. So if you think, why should you do it? Well, first, I don't have a, well, of course, you have a separate pool. You're not gonna, in your common pool, it's not going to be affected by it. Maybe if you had like a cases that, because of this thread sharing, you know, that the thread that calls it, it's also invoked, so you would have like a threads of a different life cycles. I could potentially imagine some problems with the transactions and so on. The second reason is that if you invoke the parallel stream and one of the threads gets stuck, well, it gets stuck forever. So this is something what you can influence in this case, because well, you can really define a timeout. A parallel stream, please do it for me, but actually wait only max 10 seconds. So again, this is like the reasons that could be a reason actually to go for it. Okay. If we try to draw some conclusions from the fork join framework, again, nothing more than just like a recursive divide and conquer algorithm. So as we have one shared pool with not so many threads, or basically as many threads as you have CPUs, cores, or the virtual cores, is avoid I/O. Because of course, every time you wait for something, be it like a disk or a network resource, you're gonna burn all these CPU cycles. Again, used for intensive CPU intensive tasks. So when you stick to it, then all the common pool, all the defaults, they will really perfectly make sense. Mind if you have like parallel streams, because well, if you have like a parallel stream having maybe like a for each, and in the for each you have another parallel stream, because then you might have some anomalies. We can gladly have a chat about it later. I did some tests. There is not really enough time to show it, but yeah, you can actually find out yourself that the thing will be pretty slow. And because of the worker pool, so the key why the forkjoin framework actually exists, always prefer to have more more tasks than necessary, because if you have 128 cores, but you have like 80 of mega tasks, well, you're gonna only use like, I don't know, your CPU for 60–70%. I mean, the power you have. And again, rather stick to the common pool, because it just makes sense. Okay, so this is the forkjoin framework. And right now in the example, when we were adding the numbers, you saw that we kind nice and evenly splitted our array of numbers in the left and the right part. But as you know, stream can have many sources. Actually, you can also create your own streams. So sometimes we need a way to influence how this thing is actually and get split. So when we are in this fork part, well, we need somehow instruct it, or it somehow must be smart enough to instruct itself how this thing should be splitted. And this is something what was introduced in new interface that was introduced in Java 8, which is a Spliterator, which is a splittable iterator. It even stands here, okay. And it's basically designed to go through your elements in parallel. So, yeah, to kind of apply the iterator in whatever number cores you have. So how does it work? It has actually a bunch of methods, but those are the main free ones. So, as you know, the classic iterator, it has next and next. So simply, do I have something? Do I still have something? And if yes, please give it to me. The try advance, it's kind of incorporation of those two methods. So it returns a Boolean telling you whether there is still something in your Spliterator, but it also takes a consumer that simply does something with your element that it was currently iterating through. And when you think about it, it really nicely makes sense how everything connects together, because when you work with your streams, you nicely you can use the lambdas to pass the behavior. And again, if you have a consumers and so on, they are very gently passed there. Another method, which is like the heart of the Spliterator, is the try split. So it does two things. It returns a new Spliterator, and it's changing the coverage of the current one. We also have the characteristics. Well, you split it. It's just like some hints to environment to speed up, to introduce some optimizations and so on. So let's see the try split in action, because again, it has some consequences. What should you think about when you think about the performance of your parallel stream? So we have our Spliterator. Again, be it again a huge array of numbers. So when we invoke a try split on this guy, it does two things. So first, it's returning a new Spliterator, which would be like, okay, I don't know, if the numbers are from 1 to 100, it will return it from 1 to 50. But at the same time, it's changing the coverage of this Spliterator. So this would be from 1 to 50. This would be from 51 to 100. So this is actually the whole trick it does. You do it again, and it does exactly the same thing. So on our Spliterator 1, it returns a new Spliterator, would be from 1 to 25, and it's changing the coverage of this guy, so it would be from 26 to 50. So this is the whole trick, how actually the parallel stream gets forked. And we do this thing over and over till the try split returns a null. And then we know, okay, we're done with the forking step. Now we can now the parallel stream can process this in sequentially and later join it. So when you look at the Spliterator 1, it's really this guy. It's all the time the same object. It just it got 2 times try split invoked on it, so its coverage was shrinking. The question is, can you use your own Spliterator for a stream? You can. So you have the stream support class. It's like a low-level class that you can construct streams. And Yeah, so basically you have this stream method that you pass your Spliterator. I'm not sure if you ever really going to need to do it. Again, it's good to understand how this thing is working under the hood. Maybe if you have like a enumeration, I'm not sure if you can create enumeration out, if you can create a stream out of the enumeration, would be maybe like one of the cases. If you're writing your new collection and you're not very fond of the default implementation of the try-split, would be one also like the case. Or simply if the elements in your streams, they have certain semantics that the default splitting process wouldn't make sense for you, then you can influence the process. But again, probably you're not really going to need it. Okay, so when we again stick to the Spliterator, so basically, imagine we have a linked list. We call a Spliterator on it. Well, it returns a linked list Spliterator, of course, of a type. What are my elements in the list? And right now, what we do first on our Spliterator, the main one, so really the one on top, it has 10K elements. If we try split again, it does two things. It returns a new one. So this is the one is being returned. So its size is like 1K. So you can see it on the picture, and it's changing the coverage of itself. So basically, this is what happened. And if we do exactly the same thing for ArrayList, well, we have ArrayList Spliterator. We see what is its size. We call it a try-split, and then we see what is the size of the new one and of the one that coverage got changed. And if you look at the ArrayList, it's nicely and evenly divided. However, if you look at the linked list, well, it's like this kind of mini list that was created. And why is it like this? Because, well, whenever we start a problem that we want to execute in parallel, we always start at one core. I mean, the problem is never multi-core from the start. So while actually we call this try-split, and in order to split a linked list, you really have to go through the elements. So while we're actually doing it, even if we have 500 cores, it's like 499 cores that will be sleeping, because it's only one core that really is invoking the try-split. So the guys at Oracle, they just provided some intelligent implementations depending on the data structure. It's like, okay, if I have a linked list, please, I want to actually fork off as soon as possible. So this is actually the reason why this is not so, well, not evenly divided. And this, of course, means that for a parallel stream, certain sources are more friendlier than the other. So whenever you have this, well, when you create the tree, when you go from the root to the leaves, it kind of matters what you're doing. So if we have a linked list, you already saw it again. It's you need to walk through the guy iteratively, so it can be expensive. When you use the generator function, well, it's an iterative generator. It has the same characteristics to generate the elements as a linked list. Hash set and a tree set, but something like in the middle, it's well, probably it won't be a ON. It would be like something called logarithmus, and of course ArrayList or the stateless generators, they are fine. So again, well, like one of the lessons, whenever you create a stream, parallel stream, think about the stream source. Few examples. So basically, what we have here, we have like 1 billion elements. Okay, well, let's be bold. Why not? All we would like to do is to compute their sum. So first, we're not going parallel. It's a nice sequential execution. We have like 1 second. If we all we do here if we just try to parallelize this guy with the default heap size when you start the JVM, it explodes. It actually explodes when you try to invoke the try split method on the stream source. Or even more generally speaking, if you create a linked list with 1 billion elements, you invoke a try split on it, it explodes. So yeah, because again, when you think about the overhead, it's quite heavy. If we go for a stateless generator function, which is friendly, and you do it sequentially, it's taking like 600 milliseconds. And you might actually wonder, okay, like what the heck, those two guys, they should have a kind of similar performance because they are both, it's a sequential run. So as I do it sequentially, I mean, the range shouldn't give me any benefits. Well, it does because the iterate method, it returns boxed objects. So you have like 1 billion objects that you need to box and unbox. So yeah, this really basically improves the performance by twice if you don't do it. So even though it might be like a bit confusing, okay, I have a long streams, I have a really specialized stream. This is what I read on the Stack Overflow to do, but still the iterator function always generates box objects, and the sum expects unboxed objects, and you have like boxing and unboxing very unnecessarily. So this is exactly what the range in this case has changed. And right now, if we call the parallel method on it, still we have like the thing executes 5 times faster. Okay, just check the time. All right. So findAny and unordered. So. Well, maybe the example probably explains it best. So imagine we have this kind of very simplistic stream of 6 elements, and all we do here, we just print the elements of it, nothing more, full stop. And of course, as we execute it in parallel, as it does the tree, whenever you execute it, it's producing something else, obviously. If we remove the parallel out of here, it would be nice like 1, 2, 3, 4, 5, 6. However, as it's a parallel stream, well, you cannot really predict the order. And if you like to invoke the find first method on this stream, well, the API is smart. It will always, if you invoke a find first, it will always return 1. So it will really obey to what you want. But this is an overhead, because when you think about it, okay, the kind of natural order of this parallel stream, it's random. It's this. So if I tell this guy, give me the first one, he must do some effort. Okay, what was actually your first element? So just prefer to use, if you not really worry, if you not really don't care, which one should it be? Return findAny, because find first would be like the 1, always 1. But if you invoke a findAny, it would be like 4, 6, 2. So if you don't really care about it, go for it. It will be faster. The same about limit method. So if you invoke the limit 3 on this stream, it will return like 1 to 3. Sorry, it won't be 1 to. It will be 1 to 3 as a set, not exactly in this order, but it will be always 1 to 3, 2, 3, 1, 3 to 1, and so on. However, again, this is an overhead because the natural order of the stream, the first 3 elements like 4, 6, 1, 4, 6, 4, 5, and so on. So whenever you do the limit and you have a parallel stream, like, well, think about it that maybe I don't really need the first element, so just give it a hint that this is actually unordered. I don't care about the order, so just give me any element. All right. Yeah, as a down-to-earth proof, so we have a bunch of numbers, and we just filter those that are bigger than 500K. And if I invoke the find first, well, the guy is smart. It obeys. It returns exactly the very first number that is matching this condition. However, if I don't really care about the order, if I'm interested in any, this is what I'm doing here. It's for us 4 times faster, but of course it returns an element that basically every time you invoke it, it will be a different one. Well, depending how long you keep invoke it. So again, the unordered and findAny can be also your friend. Okay. Yeah, avoiding short state. So also to think, you think about an example. So imagine we have like a accumulator class. Well, all it does, it's accumulator. So basically, it has this sum method that you keep invoking, and it's simply increasing the result. So right now, if you do this kind of thing that you instantiate your accumulator, and you try to invoke this in parallel, so basically sum the numbers from 1 to 100, well, you're going to have different numbers all the time, because you're going to have race conditions all over the place. So again, with parallel streams, it's a kind of also try simply to unlearn certain patterns, because in this case, when we have a function that maintains a state, it doesn't go so much so well along with the streams. What you can do is to make this method synchronized, but actually, well, then all the effort to have parallel stream won't be bothered, because synchronize is very expensive. When you have multi-cores that they communicate with each other, saying, okay, do this, no, don't do this because I'm doing something. This is very expensive. So all your benefits of a parallel stream will be lost. So basically, lose like a reduction function, and again, if you have parallel streams, stick to the pure functions. I'm sure there are plenty of lectures here about functional programming. So whatever you learn those there, just apply it to parallel streams. Okay, almost at the end is the sequential and parallel. So as explained, we have this. Well, a stream is basically, it behaves like a builder pattern. So it does really nothing till the very end when you call the boss, the terminal operation, please just execute me. And you might be tempted by having those two methods, that one is giving a hint, okay, when you arrive to the terminal operation, do it sequentially, the parallel one, do it, where's the laser? Do it in parallel. So you might be like tempted, okay, maybe I could do something like this. I have a range of numbers. If I'm computing primes, it's expensive, it costs time. Let's do it in parallel. However, when I have my accumulator, so you saw one slide before, accumulators are evil, you cannot really do it, you shouldn't do it, let's be smart and do it sequentially. No, it won't really work. Well, it will work, however, the whole stream will be invoked in a sequential way, so you will lose the benefits of parallelism. Okay. Sure. Shall I go back? It's a very good question. Well, this is just a matter of fact. It is like this, but they are, however, libraries that you can kind of overcome it. That you can achieve a fine-grained control. What is parallel? What is not? We can speak gladly about it. And actually, I couldn't.
This is a very good example where this fits the requirement. How to solve this? Have to break it into separate steps. Then only you can solve this.
No, you simply well in. Yeah.
The sum part has to be done sequentially because of the shared volume.
Yeah, so you really, well, if you stick to the pure JDK8, so not some other libraries on top of it, I would probably split it, or just get rid of the accumulator to have like a reduction or something. But yeah, it's something also I'm personally missing, so we can, yeah. All right, so almost at the end. Sorry, checking the time all the time, you know, coming from Switzerland, the land of watches, so well, you have to keep checking it. All right. So I think that the main conclusion is because making a parallel stream is so easy, well, it's so easy to turn your parallel stream as your stream to parallel stream, it doesn't mean you should do it. On the contrary, so always do it wisely. And well, if you have like a application that has like, I don't know, if it's big chunk of it is a parallel stream that does something, apply always those 3 steps, which is measure, measure, and measure to find out whether it really behaves as it should, because you might find that, okay, it's underperforming or it completely does something wrong. So use it for CPU intensive tasks. Choose data structure that are easy to decompose. For example, linked list is not. Choose data structure that are also easy to compose. I mean, linked list, it's easy to compose, but if you think about the hash set, if you have like a collectors grouping by, they are not so trivial to compose again. So think about it, and rather prefer it for a big set of data. So if you have like, I don't know, 10 elements in your stream, don't bother. Well, thank you very much for being an awesome audience, and have a blast in the CloudFest.